The test is not. Yeah, test the following week. Yes. Yeah. So quiz next week, test the week after that. All right, so we're in section 8.2. And we are talking about, let's get going, guys. Similar polygons. So let's remember, before we start talking about similarity, let's remember what a polygon is. What? All right, guys, let's stop talking. So polygon, what is a polygon? It's a shape, yes. What's special about it? Multiple sides? And polygons, what kind of things are the sides of polygons? Lines or parts of lines? Segments, there we go. Portions of lines, so segments. So poly just means many. So it's a many-sided shape, and our sides are segments. Now, when we talked about dilation the other day, we said that a dilation changes the size of a shape. I'm sorry, yes, changes the size, but not the shape. So that's one important thing that we're talking about in this chapter. Dilations change the size, but not the shape. And today we're going to start talking about what that means in terms of things we can measure about the shape. We've talked about how to construct a dilation using a center dilation and how we make those things. But if we have two shapes, how do we tell? How do we compare those shapes and decide if one is a dilation of the other? If one shape is a dilation of another, we call them similar. So that is going to be one of our big ideas from this chapter is when we have similar shapes. So similar shapes are dilations of each other. And we need to figure out what that tells us about the shape. If two shapes are dilations of each other, they're similar. Well, what does that mean? So we're going to come up with a postulate. So I'm going to just call it the similar polygon postulate. And what do we mean by postulate? What is a postulate? It has something to do with whether or not it's true and whether or not we can prove it. Anybody remember postulate? You were close, Maria. Yes?
Something we accept as true without proof.
There we go. Something that we accept as true without proof. It seems to make sense, but we accept it as true without proof. We use postulates to prove other things. So our similar polygon postulate tells us how we can tell if two polygons are similar. So two polygons are similar if and only if And we have two things that need to be true. The first, corresponding angles have to be congruent. And the second is corresponding sides are proportional. And this is where the proportions that we worked on at the end of last week come into play in this chapter. Proportional means they have the same ratio. So we compare corresponding sides by setting up ratios and seeing if they're the same. And let's remember that corresponding just means that they match up. When we talked about polygons before, we talked about how we figure out corresponding angles and corresponding sides. That just tells us that the angles match up and the sides match up. That's what corresponding means. Our symbol for similar is a little squiggle. I'll do that in red. So that's the symbol for similar. So it's like our symbol for congruent was this squiggle over an equal sign. So we just leave out the equal sign, and that tells us that things are similar. And the other thing that we need to talk about before we do our examples is a similarity statement. Similarity statement is just like a congruent statement that we worked with when we talked about congruence. It just matches up the letters of the vertices of the two figures. And our similarity statement tells us how the figure matches up. So an example of that would be if I had, I'm just going to sketch a couple of shapes here. If I say that these two are similar, call this ABCD and this EFGH, I would say that polygon ABCD is similar to EFGH. This is a similarity statement. Just tells how each vertex matches up. And if we're talking about the corresponding parts here, this angle A would correspond to angle E, angle B would correspond to angle F, angle C would correspond to angle G, angle D would correspond to angle H, and we can match up the sides the same way. The sides that match up are in the same order on either side of the similar symbol. Questions on this so far? All right, let's look at a couple of examples using similar polygons. So for this example, we want to figure out, are these similar? And here are the shapes that we're looking at. We have a couple of parallelograms. This side is 3.1 on each of these. This side is 3. This angle is congruent to this angle. These two angles are congruent. And the lengths of this side, these sides are 4.2, 4, 4.2, and 4. So we want to know if these two parallelograms are, and I'm missing one thing here, are similar. So we need to figure out two things. Are corresponding angles congruent? So looking at these two figures, are the corresponding angles congruent? This angle is congruent to this angle. This angle is congruent to that angle. So the angles that are in the same place on each figure are congruent, right? Andrew, stop. So the answer here is yes. Corresponding angles are congruent. There were two things we have to figure out, though, to decide if they're congruent. We have to figure out if corresponding angles are congruent. We have to figure out are corresponding sides proportional? So proportional, again, means same ratio. So we have to see if the corresponding sides have the same ratio. So let's make ratios out of the corresponding sides. If I make a ratio, what side length corresponds to the side length 3.1? 4.2. So we need to figure out, we're going to make a ratio of that, 3.1 over 4.2. If I divide that out in my calculator, that's 0.738. What side length corresponds to the side length 3? 4. So let's make a ratio of that. 3 over 4 equals 0.75. Do they have the same ratio? No. These aren't the same. So the corresponding sides are not proportional. So these are not similar. Because both of these have to be the same. The angles are okay, but the sides are not proportional. So they're not similar. Both of these have to be true for the shapes to be similar. Questions on that? Need a little more time, Tyler? Okay, no problem. So the idea here, what we're doing, is we're saying that we have to have the same scale factor between these two sides and between these two sides. So the scale factor has to be the same for them to be similar. We're multiplying the sides by each side by the same scale factor in order for them to be similar. So this is kind of stretched unevenly between the up and down and the side to side. That's what's going on here. All right, you good? Okay. Now for this one, we know that our figures are similar, and we need to figure out a missing side. So for this one, our polygon ABCD is similar to WXYZ. And let me draw my picture here. And here's ABCD. Or sorry, this is WXYZ. And the sides of WXYZ, this is 10.5. This side is 14. This side is 7. And this side is 7. And here's ABCD. And with these, we go by what the problem tells us, not by how it looks, just like we did when we talked about congruent polygons. And we don't know the length of DC. So that's what we want to find. We want to find the length of DC. So we're trying to find the value of x. So we know that these are similar. Because these two shapes are similar, the corresponding sides have the same ratio. So let's figure out our corresponding sides. And I'm going to switch this around, and I'm just going to say CD, because that's how I have it written up here. Doesn't matter which order to find the length. So let's figure out which sides on this figure correspond. CD corresponds to, if it's hard to tell from the way the figure's drawn, we can always go to the similarity statement. And that tells us how they match up. So what do you say, Tyler? YZ. CD and YZ match up. So CD corresponds to YZ. Let's match up all of our sides. AB corresponds to which side on the other figure? WX. AD corresponds to which side? WZ. We're just matching up where they are in our similarity statement. And finally, BC corresponds to XY. And the fact that they're similar tells us that all of these corresponding sides have the same ratio. So let's make a ratio between the corresponding sides, and because they have to be the same, we're going to say they're equal. So I'm going to say the length of CD, which we don't know, is x. Make a ratio with its corresponding side, YZ, which is 7. Sorry, that was XY. YZ is 14. X over 14 has to be the same as the ratio of any other two corresponding sides. So let's pick AB. AB is 2. And we're going to match that up with WX. WX is 7. They have to be the same ratio because they're similar. And here's our proportions that we worked on the worksheet solving the other day. That's why we practice so much with those, because we're going to work with them in similar figures. We cross multiply to solve this. So I get 7x equals 2 times 14. So 7x equals 28. Divide by 7. And x equals 4. So because these two shapes are similar, the corresponding sides have to have the same ratio. So that tells me that x has to be 4 to keep these ratios all the same for all the corresponding sides. Questions on that? Yes?
Well, if you kind of know that 2/7 if you multiply by 2 it is 4/14, can you just do that just 2 times?
Sure, you could, rather than cross multiplying, you could say 7 times 2 equals 14, and so 2 times 2 equals 4. So that's our scale factor, right? It's the same idea. And if you wrote that as an answer on a test, I would be perfectly fine with that. Okay? All right, any other questions? That's a good question. Sometimes it's not quite as easy to pick out. But in that case, yeah, that would be fine. All right.